A very good day to all my lecturers for SIF1006 Practical Physics 1. My name is Eugene, and in this video, I'll be explaining all the experiments which I've carried out throughout the semester. Now, the first experiment is M1, tension and kinetic friction. In this experiment, when a string is pulled around a curved segment with no acceleration, the produced friction is equal in magnitude but opposite in direction to the tension created by the pulling force, which results in the equation shown on the right. Now, two equations can be substituted into the first equation, which describe the produced frictional force as well as the normal force in the case of a very small angle, thus producing the equation shown below. When we take this equation and integrate both sides, the resultant equation is produced as shown on the right. This is known as the capstan equation, which describes how as a rope is wound around a post, the produced frictional force increases, which in turn acts against the tension exerted by a load. To carry out this experiment, one end of a string is tied to weights, while the other end is tied to a spring balance. Then, in increments of 45 degrees, the tension exerted by the weights are measured and recorded from angles 0 degrees to 360 degrees using the spring balance. The measurements, which are in grams, are then converted to newtons, and these steps are then repeated with angles 360 degrees to 720 degrees. After plotting out the graph for the two different sets of angles, I find that the values of T naught, which is the tension caused by the weights, are the same for both sets of angles, whereas the values of mu, which is the friction coefficient, are different for the two conditions. Thus, the relationship between tension and kinetic friction along a string segment has been verified as the capstan equation, as shown below. This equation can actually be arranged into the following form shown on the right, making it a convenient method for measuring the friction coefficient. The second experiment is known as DC1, measuring the internal resistance and the precision of a galvanometer. This experiment is actually composed of four different parts, from DC1A all the way to DC1D. The first part is known as measuring the internal resistance in a galvanometer. When creating electrical schematics, it is typically assumed that the components are ideal and allow all current to flow through them. However, all components actually exhibit some level of resistance, which is known as internal resistance. The internal resistance can be calculated by setting up a potential divider and then using the formula shown on the slide. The second experiment, determination of galvanometer sensitivity. The sensitivity of a galvanometer can be explained as the current required to deflect the pointer needle by 1 unit on the galvanometer scale. This is expressed as the equation on the right. However, to find the value of Ig, we can use the equation shown below, as the galvanometer does not have any defined units. The third part is voltmeter in parallel with resistor and ammeter. Electrical components like voltmeters and ammeters have internal resistance, as stated previously, due to a coil inside of their mechanisms. The small resistance of the coil impedes the current flow, and if left uncorrected, the readings measured by the voltmeter or ammeter will be inaccurate and smaller than the actual value. For part D, voltmeter in parallel to resistor only, we use an alternative method to calculate the actual resistance of a resistor. This time, the voltmeter is connected in parallel only to the resistor. And instead of the internal resistance of the ammeter, the internal resistance of the voltmeter is used as a reference point. So how did I conduct these four experiments? In the first experiment, the circuit is set up as shown in the figure, with R1 and R2 being 470 ohm and 10 ohm resistors. The deflection on the galvanometer due to the current Ig is recorded with the decade resistor box set to 0 ohms. The decade resistor box is adjusted so that the new current flowing through the galvanometer, Ig prime, becomes 1 over N of Ig, where N is equal to 3, 4, 5, and 6. In the second experiment, the circuit is set up as shown in the figure. The resistance of decade resistor box is adjusted until a full-scale deflection is obtained on the galvanometer. The current, Ig, and sensitivity, S, are then calculated using this value of Rx. For the third part, the circuit is set up as shown in the figure. The value of resistance is calculated by using the current and voltage readings across the resistor. Two different methods are actually used to find the current and voltage readings, and their results are compared. For the fourth experiment, the steps are actually similar to the previous experiment, except the value of resistance is calculated by using the current and voltage readings only across the resistor. The same two methods are used, and the results are also compared. Now, here are my findings for all four of the experiments. Now, let's move on to the third experiment, AC2, determination of impedance of inductor and capacitor using an oscilloscope. In an ideal RL circuit, the voltage across the circuit, VRL, can be illustrated with the phasor diagram below. However, in real-life circuits, the inductor also has an internal resistance, RL. Hence, we have to correct VL as shown as the second phasor diagram. Thus, the formula for the inductor's impedance and inductance are shown with the two equations on the slide. Similarly, in the case of an RC circuit, the phasor diagram also needs to be corrected. And drawing from the derived expressions of the case of the RL circuit, the following equations are obtained for RC circuits. In order to carry out the experiment, the circuit must first be set up as shown in the figure. The decade resistor box is adjusted to a value of R equals to 5 ohms, and the decade inductor box is adjusted to L equals to 20 millihenries. The values of VR, VL, and VRL are measured using the oscilloscope and recorded. The values of L and ZL are calculated. Then, the experiment is repeated with a 0.47 microfarad capacitor instead of an inductor in order to find C and ZC. Now, here are the findings that I got from carrying out the experiment, as well as the final calculated values for the total impedance of the inductor, as well as the inductance, whereas this is the data for the RC circuit, as well as the calculated values of the impedance, as well as the capacitance. Now, let's move on to O2, refraction of light. Snell's law states that when light passes from one medium into another with a different density, its speed changes. However, different wavelengths of light are actually slowed down by varying amounts, even though they are propagating through the same medium. This explains why polychromatic light splits into its constituent wavelengths when refracted through a prism. The dispersion of a prism describes the change in refraction of light with respect to the material of the prism. The equation for dispersion can be described with the following equation. whereas the equation for the dispersive power of a prism is given by the following equation shown on the slide. Now, in this experiment, there are actually two parts. And in the first part, I measured the angle of the prism. The apparatus is set up as shown in the figure. The telescope is rotated to the first arc position, and the reading on the vernier scale is recorded. Step 2 is then repeated at the second arch position on the opposite edge of the prism. The angle between the two slit images, 2A, is calculated and then used to calculate the angle of the prism, A. Moving on to the second part, I then determine the dispersive power of a prism. The angle is angled so that the illuminated slit shines through the frosted edge of the prism. The telescope is rotated until the 7 colored line spectra can be seen through the eyepiece. The angle of deviation for the 7 colors on vernier scale A and vernier scale B are then recorded in the table. Here you can see the measured values which I have obtained and tabulated. When I plotted out these values, I found that model 4 is the best fit for the data. And by using this model, I managed to find the dispersion of the prism as well as the dispersive power, as shown on the right-hand side of the screen. The last experiment is N2, rigidity modulus of wire by using Maxwell needle method. The rigidity modulus describes the stiffness of a material. Fortunately, without having to bend the material, we can actually find the rigidity modulus by using a Maxwell needle. This is done by using the difference in periods of oscillation, T, when the configuration of the Maxwell needle is changed, as shown below in the equation. To carry out this experiment, a wire is attached to the Maxwell's needle and hung on the retort stand. The solid and hollow cylinders are inserted into the Maxwell's needle following configuration 1. The Maxwell's needle is twisted and released, and the time taken for 10 complete oscillations, T, is measured and recorded. Steps 2 and 3 are then repeated following configuration 2 instead. The resulting data for both configurations are tabulated and then used to calculate the rigidity modulus. And as you can see here, I find that the calculated rigidity modulus of the wire is 60.6 plus minus 14.4 gigapascals. And with that, I've reached the end of this video. Thank you for watching to the end, and I hope that you enjoyed this as much as I have. Thank you.